Hello, RF Dude here. Today I want to talk about network analyzers and show you how to use one of those boxes. Network analyzers are one of the most common pieces of equipment in RF labs nowadays, and you can measure all kinds of different parameters like gain, insertion loss, return loss, group delay. So what we are using nowadays are commonly referred to as vector network analyzers or VNAs. The word vector already implies that those network analyzers are capable of measuring phase as well as magnitude, opposed to older scalar network analyzer systems that are hardly used anymore nowadays. It used diode detectors, and they were only capable of measuring magnitude and return loss, but no phase relationships. So basically, network analyzers are manufactured by different companies. The biggest ones probably out there are Agilent or now Keysight. It's been one of the oldest manufacturers of vector network analyzers. Then there's Enritsu, which used to be a Wiltron company, and then of course there is also Rohde & Schwarz, which is a German company, and those three companies are pretty much dividing up the market in between those three big players. So generally, when we talk about network analyzers, there are different kinds. The ones that are commonly referred to as RF network analyzers, and then there are microwave network analyzers, and usually the RF analyzers are offering a frequency coverage to 3, 6, or sometimes 9 gigahertz, but extends the lower frequency edge down to 30 kilohertz or even 9 kilohertz, depending on the model. The microwave analyzers usually start at 10 or 45 megahertz, but can cover frequencies up to 50 gigahertz, newer model 67 gigahertz, or even 100 gigahertz, and then using external frequency extenders, they can cover all the way up into the terahertz range. So, but it's a pretty expensive game up there. So this specific network analyzer I got right here, it's an 8753D with option 11, which basically option 11 means that it uses an external test set. So those analyzers have been around for quite a while, and the 8753 especially was a very popular model that was produced by Hewlett Packard and then later on Agilent for a long time, and there are tons of them out there on the surplus market and found their way into home labs because they have gotten fairly reasonably priced over the last couple of years, and they are pretty reliable and what we used to refer to as workhorses. So they are also pretty much still serviceable, like the new piece of equipment. And overall, it's a pretty decent box. This specific model covers to 3 gigahertz. And we got over here, we got the display, which is a 9-inch CRT display. It's pretty easy to read, even under adverse light conditions. And then we got the test set on the bottom. So generally, what can we measure with this network analyzer? If we press the measurement button right here, it gives us a overview of what we can do. So it basically is, we can measure reflection, which is S11. We can measure transmission, which is S21, reverse transmission, which is S12, and then reflection, which is S22. So generally, for the ones who are not familiar with S parameters, generally when you when you characterize microwave parts, then it's common to do it in terms of S parameters, and S parameters are actually complex parameters that include magnitude and phase information. And if you do RF design, you come across S parameter files for your active devices that are used in simulators or even as a Smith chart to design matching networks. As vector network analyzers can measure S parameters, and if you look down here, what's S, is 1, 2, or 2, 1, or that refers basically to your ports. So you basically have port 1 over here, you have port 2 over here, and then you got little diagrams that shows you the direction. So basically S21 would basically be the direct signal flow from port 1 to port 2. Then S12 the signal flow from port 2 to port 1, and then S11, S22, or reflected parameters, which is basically what you may be familiar with under the term return loss. Then we have down here, we can also switch over and basically do ratioed measurements in between the different ports, or even measure the power on each port. So and then we got conversions here that we can measure. So as far as the measurement format, we can change this as well. So we can basically do logMAC, which is this format, which is the easiest one to look at and interpret. So we can measure the phase, display group delay, or we can also do a linear measurements, SWR display, or we can do real and imaginary impedance measurement. Then the other another common form display would be a Smith chart right here. So a lot of people that are working in the RF field are probably familiar with that one back in the old days when you were actually still doing your matching networks using the Smith chart. So as far as using this box, it's actually pretty straightforward. We got the front panel over here, nicely grouped. We can select the measurement channels, channel 1, channel 2. The response basically is everything that refers to the receiver part. So we can select the measurement format, scale reference, which is basically how many dB per division. We can do averaging. We can select our markers, and then of course we can also turn on like dual channel display. We can put channel information into memory and do memory operations. So there's a whole variety of different measurements we can do here. And then we got our markers, and you can select which marker you want. You can select the delta marker, which is basically if you measure the difference in between two markers right here. So that's your delta marker. And then down here is our stimulus area. Stimulus is commonly referred to as a signal source. So you can select the power. If you have a network analyzer 8753 that pretty much has a built-in test set, since this power, you can select it all the way down, minus 90 dB, I believe, because there's a step attenuator built in. But this one doesn't have the step attenuators in the test set, so you basically select the source power, and then down here you can select the step attenuator, and just you hear click when you turn. And then another feature here is power trip. That basically, if you measure a amplifier or something and the output power exceeds the safe range for the test port, basically it has a built-in fuse that trips, and then you can reset it here. And the last but not least, we got those functions down here: system, that has your different things like setting the clock. You can set limit lines if you do measurements. You can turn on time domain measurements, all that, but it's all more advanced stuff. And then you have a service menu where you can run internal self-tests. You can look at your options. You can look at what firmware revision you have installed and what options. And then last but not least, you got the preset button. If you're just completely lost, push something so you're not supposed to push, press the preset button, you're all good. You have safe recall. We can basically save instrument states or settings. And then you got the copy button, and basically this, well, it's you can connect a old parallel port printer to the bag or a plotter, and that you can basically do screenshots of your measurements. So what I want to do, I want to show you how to do an actual measurement here. And so basically what we need is we need a couple of things. So basically down here what we have is we got a torque wrench, and that's one of the most underappreciated pieces. Then we got a regular little wrench, show you what to use this for later. We got a 3.5 millimeter female to female adapter, and then we got this little puck here, which is basically calibration standards, which is an open, a short, and a load. And we need this to calibrate our network analyzer. So the first thing I do is I press the calibrate button here, because I believe we want accurate calibrated measurements. I select CalKit and I select 3.5 millimeter D, and then press return, and I go to the calibrate menu, and I want to do a full 2-port calibration. So I'm just going to start with reflection, and basically it asks me now to connect those different standards. I'm going to start with port 1 and basically connect the open. Now we use this little wrench here basically to hold this adapter while we are torquing the open standard to the right torque. We go up here, we're gonna press open, and then we're gonna move on to the short. So short is connected. Now push the short button here, and we're done. So now I'm gonna do the rest of it. Basically, if you get the picture right now, you just connect open short load for the 2 ports, press the button, and wait for the sweep to complete. Now, once we get done, it says press done if we are finished. So I'm gonna press standards done. And it now goes back here and says additional standards needed. So we're gonna go to transmission, and basically for transmission we just connect a through adapter right here. So through is connected, and now I'm gonna start here with transmission, forward match through, reverse match through, and okay, now I got all this done. I'm gonna press standards done. Isolation we're not gonna do right now. For this you need basically would need 2 terminations to do isolation calibration. And so I'm done with 2-port, and hold on. So I'm done. One little information I forgot here, we actually have to press isolation and then click omit isolation for this firmware revision. It won't let me just skip it. Okay, so now we got all this highlighted here. We press done, and so press save, recall the save cal data. So we're gonna press save, and we're gonna press save state, and so now we're done. So you can recall this calibration later on if you need it. So now we see we got a nice straight through line. If we're on S21, it's the way it's supposed to look. And so now let's connect the device on the test. So I got something connected now, and that's basically a filter. It's a high pass filter. So what the calibration basically does is it moves the reference plane to the reference plane of your cal standard. So in this case, the reference plane would be a little bit off because I used this adapter. So basically, reference plane wouldn't be right here, it would be at the end of this adapter. Normally you should use a cal standard that has the same sex as your device on the test, but I only unfortunately have a male calibration standard, so I kind of have to work around it, but normally there are ways around it, but right now this is just for demonstration purposes anyway. So this is how our response looks like right now. So now I'm gonna press marker, and I'm gonna put some marker up here, and so now we can see basically up here, let's see, it says we are at 1.3 gigahertz and 1 dB down, and that basically always refers to this red line in the middle. So at 1.4 gigahertz, because it's a 1.4 gigahertz high pass filter, we are 0.55 dB insertion loss. Then now we can use a delta marker. Basically go delta menu, reference to marker 1, and then basically go select marker 2, and so now we can see basically the delta in between those two markers is 208 megahertz. So let's go to select 200 megahertz, and now we can see up here that we are basically 28 dB down. So basically, see, marker 2 would be 28 dB down compared to the level of marker 1. We can switch this over, look at S11, and we can see, okay, we got a nice match here, because as you would expect for a high pass filter, it's basically says very poor loss below the cutoff frequency. So at 1.4 we really have nice return loss right here at 1.4 gigahertz. And of course you can also enter this stuff over the keypad. You can enter 1.4 gigahertz, and so now see it's minus 27 dB return loss, and we can go over to S22, measure the output match as well, and then of course we could also go and measure the group delay, or we can measure the phase of this filter. And so one more word of caution with this specific analyzer is if you change the power after you calibrate it, then pretty much your correction will become invalid if you go outside of the range of the source. So see, now it says source parameters changed, which basically means your correction is no longer valid, and so you would have to recalibrate it. So that's pretty much it as far as the general use goes. There is another little feature right here which is power meter calibration. This is basically a function that you can use an external power meter that's connected to the GBIB interface, and you connect the power sensor to your test port, and run a calibration sweep, and then basically it calibrates your test port power, and it gives you a little bit better accuracy of your power that you have on the air. But generally it's not something you want to use, and so pretty much that's all I have for now. That's all I have for today. I hope you enjoyed this video and find it useful. Thank you.